Hey, so welcome back. Weather wasn't so bad after all. Better or worse. Okay. We're looking at seesaws. The topic is seesaws, and underneath seesaws is a whole world of rotation. So just to take a very quick review, just as you saw inertia in translational motion, there's inertia in rotational motion. So if you've got an object that is experiencing no torques, so it's free of torques, and it meets a couple of other criteria, it's rotationally inertial. That is, if it's at rest, it stays at rest. It can be oriented however you like. And to the extent that this is free of torques, it's not perfectly free of torques, but it's pretty close. It can remain at rest at any angle you like, or it can be moving with an angular velocity. And it just keeps that angular velocity. So it's just inertia in action for rotation. Any questions about the inertial idea for rotational motion? We will see pretty soon that the world of inertia and the Newton's first law that's associated with it is a little complicated for rotation. I showed you the wobbling problem a little bit last time. The other problem is the changing shape problem. And pretty soon we'll look at what happens when an object that's rotating does change shape. It turns out it can change its angular velocity, even without a torque, if it changes shape. And that's very useful for things like doing a somersault in the air when you're diving. The fact that you can change your shape and you consequently spin at a different rate is critical to the whole sport of diving or anything like diving, gymnastics as well. Okay, so that's rotational inertia stuff. And the physical quantities that show up are analogous to the ones in translation. There are velocities and accelerations and masses and all that stuff. Where I left off last time, I'm really trying to bring it into to talk about seesaws and get the job done here, is seesaws are about rotation. The two kids riding a seesaw sit at opposite ends, which we'll discuss in a minute, and they rotate the thing back and forth. It doesn't rotate continuously because eventually it hits something. So it's got a limited range of rotation, but it's all about that rotation and changing that rotation by way of torques and so on. Well, where I really left off last time was looking at the origin of the torques on a seesaw. And first off, the seesaw by itself should balance. When you walk up the seesaw, no one's sitting on it. It's typically balanced. And what does balanced mean? Balanced means that it is experiencing zero torques. And in particular, zero torques due to gravity. And just as a summary of the piece that I did in the lecture video, the online one, there are two interesting centers that objects have. One of them is center of mass, one of them is center of gravity. And let me take a few seconds to talk about those two. The center of mass of an object is the point about which its mass is evenly distributed. That oversimplifies. That's a very simple statement of its mass is evenly distributed. It's a tricky problem, but if you look at the ordinary mass distributed in an object, about some point, there is a point at which that distribution is beautifully arranged, so that you get that point becomes the natural pivot. In effect, it becomes the location in which the object's entire mass is centered. If you want to simplify the object to a single point, that's the point for its inertial type motions. And that's the natural pivot. If you spin it, that is the point that travels in the arc of a falling ball if you throw it, and so on. Center of mass. It's an inertial issue, so that you don't even need to have any gravity around to find that point. Just go into, you're in deep space, give that thing a spin, and watch what point sits motionless. Or either motionless or moves at constant velocity if you actually accidentally gave it some overall velocity. That point's the center of mass. So it's inertial. Gravity has nothing to do with the story. Okay? The other point that's interesting is the center of gravity. And the center of gravity is the effective location of an object's overall weight. If you want to highly simplify the object down to one point and say this is where the object's weight acts, that's the point. All right? It's a gravity story. Get rid of gravity, center of gravity means nothing. that said, those 2 points coincide here on near the surface of the Earth. If you go looking for the object's center of mass, its natural pivot, and you go looking for the center of gravity, it's the point at which its weight is effectively located, they're the same point. That's not a coincidence. It happens because every kilogram of mass develops a 9.8 newtons of weight here near the surface of the Earth. They go together. They're not the same idea, but they go together. And so if you look at wherever the mass is distributed, that's where some of the weight is distributed. And it all works out, and the center of gravity and center of mass are the same spot in any normal object around here, the surface of the Earth. All right? Therefore, people use those 2 words interchangeably, which is, I mean, it's okay. It's careless, and sometimes it's like, no, that's not what you mean. You're talking, anyway, they do it. They are different concepts, okay? One's a gravity concept, one's an inertia concept. If you want to know are there ever exceptions to the case where center of gravity and center of mass are at the same point? And the answer is yes, but you need, for that to happen, you have to be in a situation where the fact that gravity is not perfectly uniform everywhere in the universe is noticeable. For example, here on the surface of the Earth, the gravity is the same here as it is here, as it is here for all practical purposes. And therefore, wherever the mass is distributed, that's where the weight's distributed, and it doesn't matter that you're here, there, a little bit different. But if you look at the moon is so big. It's experiencing the Earth's gravity right now, and it's therefore orbiting the Earth. It's actually in free fall towards the Earth. It's going sideways so fast that it misses the Earth. It goes around in orbit. We'll talk about orbits down the road. But it's falling toward the Earth. Actually, the Earth's also falling toward the moon. They're falling toward each other, and they're doing a dance around each other. Okay? But the point of bringing this up is the fact that the moon is experiencing the Earth's gravity, but because the moon's so big, the near side of the moon experiences stronger gravity than the far side of the moon, and it's a non-trivial difference. Therefore, an astronaut that came to our side of the moon and stood there and, how hard is the Earth pulling toward me? They would have a certain Earth weight. They go to the far side, they'd have a slightly less Earth weight because they're a little farther from the moon. The Earth. As a result of this, the moon's center of mass is essentially its dead center. If you took the moon and gave it a good spin out in deep space, it would spin about a center mass. But the moon's center of gravity is a little closer to us than that, because the Earth's gravity is a little stronger on this side of the moon than the far side of the moon. Therefore, the center of its weight is a little closer. Is that okay with people? So there's an example where center of gravity and center of mass are displaced from each other. They show up in sort of celestial scale stuff. But down here on Earth, they're located in the same place. The center of mass of this board is pretty much right there in the middle of the board. I put the pivot right through it. And that's its natural pivot already. I'm supporting it at the natural pivot. It makes life very simple. At the same time, the board's center of gravity, the effective location of its weight, is also right dead center. And as a result of that, being right there dead center, right where the pivot is, that weight produces essentially no torque on the bar. It doesn't twist the bar, and that's where I'm heading now, is that weights, which are forces, can produce torques on things. Even though a force and a torque are different, a force is the influence that causes acceleration. A torque is the influence that causes angular acceleration. You can produce one with the other, and that's where I'm going. So weight, the weight of the board, can produce a torque on the board. For example, if I take this board off center like this and let go of it, its weight's going to be right about here. That's the center of gravity, right there. And yet, the center of rotation that I'm enforcing is off to the left. And as a result, I let go. Of course, it's going to go bang, right? Bang. That was its weight, the board's weight, being shifted effectively 10 inches to the right of the pivot. That weight, therefore, produced a torque on the board and caused it to undergo angular acceleration. In this case, this way, away from you, using the right-hand rule, whether you can follow it or not. All right? So, that said, I'm going to ask you a question using the, I'll turn on the Gidgee here. Ta-da, okay. So if a child sits, oh, okay. I'm sorry, I thought I blew something up myself. Okay, if a child sits on the right side of the seesaw, the child produces a torque on the seesaw in which direction? You got the question, okay? Questions about the question? Give it a shot here. Oh. Start. And still, oh, come on. There we go. Yeah, the right hands are out. There's always a problem with people who are left-handed and want to use their left hand. Don't use your left hand. It's backwards. All right. I'll give you till sort of little after the 30-second mark here. 5, 4, 3, 2, 1. I'll pop the polling up while you're still choosing. Oh, man. Okay, now you guys get to argue it out. You can still change your vote. We can watch the little bars go up and down. You talk to your neighbors and stuff. First off, what's the rotisserie axis of the torque? The direction you choose better be along the rotisserie axis of what happens as a result of this torque. It is a torque, not a force that we're looking for. That didn't seem to help. Well, all right. I'm going to call it here, and I will tell you, okay? The majority of you, alas, are choosing the wrong answer. It is not the purple D. No. The force is downward. We put the kid over here on the right. Okay? And the force that the kid exerts on the board will indeed be downward. That's so far, if that's what you're voting for, fine. That's true. However, that downward force results in a torque on the seesaw, and that's what I'm looking for. It twists the seesaw. In which direction? Well, the seesaw, let's watch the angular acceleration, and again, I'll try to do it a little quietly here. Ready? Get set. Okay? It rotated like that. It rotated like this. Well, the angular acceleration, that's the ultimate, the eventual angular velocity is like this. This happens to be an angular velocity away from us. Are you okay with the fact that that's away from us, using the rules? Certainly, the rotisserie axis is definitely toward you and away from you, and according to the right-hand rule, this happens to be the away from you version of it. So that's the angular velocity. That means that this board underwent angular acceleration away from you. It went from not rotating to rotating like this. It must have undergone angular acceleration away from you. Okay? And angular acceleration is caused by net torque. And it's in the direction of the net torque. So this board, when the kid sat on the right side, must have experienced a torque away from us. That torque away from us caused angular acceleration away from us, which caused angular velocity to accumulate away from us. You okay with that idea? Now, how did this come about? It came about because this board is acting as a lever. So levers are a common tool in everyday life, but they're also just part of physics. And the fact that the kid pushed out here at a distance from the pivot, not only is it a distance, it's actually got a distance and a direction. It's a vector away from the pivot. And that vector from this point, which is the pivot, to where the kid pushed. So visualize it as a little arrow pointing to the right. Now, I think I put arrows in some of the animations I put online. That arrow pointing that way is called the lever arm. It has a length, which we care about, and it has a direction, which we care about. It's to the right. And the kid goes out to a lever arm, defines this lever arm, and pushes at right angles to it with the kid's weight. And that produces a torque. That's how you make a torque with a force. Go away from the pivot, or the center of rotation, the place that you're trying to make rotation occur about. Go away from it to obtain a lever arm. And then push, not along the lever arm, either parallel to it or anti-parallel, which is maybe physicists or mathematicians speak. If you push toward or away from the pivot, that doesn't do anything. Just like if you grab a doorknob. Look at a door. So door's my go-to example. When you're opening a normal door, the one that swings about hinges, to make it rotate, or to begin rotating, you can't push it at the hinges. You need a lever arm. If you push at the hinges, the lever arm has no length. You can't produce a torque there. So don't push the hinges. You've done it. You've done it and failed. It's no fun. So you're used to trying to figure out, okay, which side of the door am I supposed to push on? If there's a doorknob, it's obvious. If there's no doorknob, it's a little bit of a check. Like, Okay, so you go out there, and you now have a lever arm, and you want to push on it. You do not want to push it toward the hinges or away from the hinges. That won't do you any good at all. Again, no torque. Push at right angles to that lever arm, perpendicular to it. That produces a torque. And the torque you produce, you can calculate it. I mean, this is one of these, people have asked me, what formulas do I expect you to remember? And it's going to turn out to be really the formula for work, the fact that you do work by exerting a force on something and having it move in the direction of your force. That formula I care about. Newton's second law I care about. That the acceleration of an object is equal to the net force on it divided by its mass. And the other formulas, you can see them. They're worth knowing they exist. I'm never going to test you on them. Okay? So this is one case in point. I'm not going to have you calculating torques produced with forces. With forks. I don't know where that one came from. Okay, so this kid, by going out at a lever arm toward the right and pushing down, which is at right angles to that lever arm, produces a torque. And the torque is, because these angles, the lever arm and the force are really truly at right angles. If they were not at right angles exactly, it would get messy. We'd be using trigonometric functions and stuff. Okay? They're at right angles. Life is simple. The torque is simply the product of the lever arm times the force, and the torque has a direction. What's the direction? It follows a complicated right-hand rule. My version of it is have your index finger point along the lever arm, your middle finger or your remaining fingers, whatever you want to do, pointing in the direction of the force. Your thumb gives you the right hand. Your thumb gives you the direction of the torque. In this case, it's away from us. Is that okay with everybody? And if I put a second kid, if I take that kid off and put a second kid over here on the left, of course, they produce a torque in the opposite direction. And it's obvious that it happens. If I do it, we'll get a bang, and the rotation will be toward you. That's the other way. The first kid over there on the right produces a torque away from you. This one produces a torque toward you. Using the right-hand rule story here, the lever arm is from this pivot to the left now. So there's my index finger. There, my other fingers are pointing down in the direction of the force, and my thumb is showing us the direction of the torque, which is toward you. And so why does the seesaw do what it does? And why do you have to sit the way you have to sit? It's because if you put two kids on the seesaw at once, they both exert torques on it, but in opposite directions. And if they're careful where they sit, they can make those torques cancel one another and be inertial, rotationally inertial. Okay? And the rest of the story is kind of obvious. Like, suppose instead of having two kids that are the same, you know, you got the big kid from down the block, or the block kid from down the, whatever. Okay, some terrible pun. All right. This kid, obviously the kid sits over here. That kid over there is going to be up, he's stuck up in the air forever. I think one of the reasons why seesaws have sort of disappeared, apart from apps completely killing them. No one wants to do anything on a playground anymore. It's the other thing is that this kid gets bored. The little kid there goes and swallows his or her gum, bites off her tongue, or you know, something terrible. Okay, but the big kid can actually balance the little kid by sitting really close in. Come on, where are you? Here, it's coming. It's right by here. All right, you know, or this is the parent with a little kid. You get used to it. You'll be doing this sometime if you can find a seesaw. So this is a little tricky for interesting but irrelevant reasons. The balancing here works again. Again, the meaning of the word balanced is zero net torque, and that they've managed to arrange it. The little kid is canceling the big kid's torque. They're in opposite directions, equally strong. The reason the big kid has to get in close is because the big kid is going to exert a huge downward force. And therefore, to reduce the torque the big kid exerts, you need a smaller lever arm. But the product of the lever arm times the kid's weight on the right is the same as the product of the lever arm times the kid's weight on the left, except for the direction. The directions are reversed. All right? That's really the story of seesaws. Is it true that waves on the ocean are created by the gravity pulling created by the moon? The tides are primarily due to the moon and the moon's gravity. The sun is also involved to a lesser extent. To give you a preview of this, if I pull it off and stop getting bogged down, we will look at tides in dealing with how the ocean works in general. And the short answer, the short story of why the Earth, why we have tides, is because the moon's gravity does pull on the whole Earth. But because the Earth is so big, the moon's gravity is a little stronger on the moon side than it is on the far side of the Earth. So the moon's pulling the water, the whole Earth, including the water, extra strong on the side nearest the moon, and extra weak on the side farthest from the moon. And the Earth as a whole is falling towards the moon, but the water close to the moon and far from the moon gets stretched out. The water that's very close to the moon bulges out toward the moon because of the extra strong gravity there. And the water farthest from the moon bulges out for a more interesting or complicated reason. It's in part left behind by the rest of the Earth, falling faster toward the moon than it wants to fall. That water out there on the far side would prefer to be inertial and go straight. But the moon's gravity does pull on it, not as hard as everything else in the Earth, and so everything else in the Earth heads toward the moon faster than the far side portion of water. Is that okay? It bulges out there too? Two bulges. And as the Earth rotates with these bulges, the bulges appear to move on Earth. So as the Earth goes around, one full rotation every approximately 24 hours, the bulges show up sort of somewhere around the equator is the worst bulge. The bulge, so I'll be the Earth, you guys are the moon, okay? So there's a bulge here, and now as I rotate, the bulge is moving, and the bulge is moving and moving. And so, but there's a bulge over here. So I'm out of hands and stuff, but when if you live on the side of the Earth that's closest to the moon, initially you're in the middle of the bulge, and then the Earth rotates, and now the two bulges are 90 degrees away from you. You're in a dip, and then you're in the bulge again, and then you're in the dip, and then you're in the bulge again. So you get high. This is high tide. This is low tide. This is high tide. This is low tide. You get two pairs every day, approximately. It's a little more complicated than there is some delay in when the bulges show up because the water actually has to move. You can't just make the bulge out of nothing. The water actually has to flow to get in the bulge. And so the tides lag behind this rotating motion a bit. And it depends on where you are. They can lag a lot behind or a little behind. And you can get other funny things that happen with the water sloshing around. There are certain locations where there's a sloshing effect as well. And you get extra big tides, like the Bay of Fundy in Nova Scotia. It has super giant tides. Okay? Little sidelight there. Okay, so this is the story of seesaws. Any questions about the basic idea of a seesaw? I think I've done it. Anything I've left behind? I left a question behind. Get this out of here. Not that one. Oh, I'll ask 2 questions. I'll try this question. It doesn't have anything obviously to do with the seesaw, but it's an interesting observation too. And that is, if you've got 2 kids, one's twice as tall, you and a kid. The kid's much shorter than you are, okay? So the 2 of you and the kid, I'll set this aside. You and the kid lean out to the same angle over the pool. I put the pool in there so nobody gets hurt. Politically correct here. And then you both let go at the same moment and tip over into the pool. Who hits the water first? So you okay with the question? You or the little kid? See what you think. I should have put that you both hit it at the same time as a third option, but I didn't do it. Now, of course, all right. I'll give you to the 32nd point, and then we'll see what you guys think, and I'll show you. All right. 3, 2, 1. Oh, a little bit of majority. Yes, see. Yes, always fun. Okay. So here's you. Here's the kid. The 2 of you lean to the same angle. Ready? Get set. It's not even close. The kid hits first, way ahead of you. The longer the stick is, the longer it will take to tip over. And so, why is this? Well, here's the story. That these 2 objects, I'm forcing the pivot to be here at their feet. These 2 objects each are experiencing a gravitational torque, a torque due to gravity. They each have an effective location for their weight, which is halfway between the 2 ends. Not surprisingly, it's pretty much dead center. That's the effective location of the weight, the center of gravity of the stick. And it produces a torque because there's a lever arm, right? It's not quite at right angles, but it's good enough. Who cares? It's close. Okay, so this is experiencing a torque, and the torque is equal to, or very close to, the weight of the stick times the length, half the stick's length. Is that okay? If I double the length of the stick, first of all, it's got twice the weight, and the lever arm is twice as long, because now the center of gravity is in the middle of the twice as long stick. So we've doubled the weight, doubled the lever arm, that's 4 times the torque due to gravity. Is it okay? And you can feel this. If you hold these 2 things there, and you try to fight that torque, this one's really twisted me 4 times as hard. It's not, can I tell 3.9, 4, no, but it's clearly in like a factor, it's not a factor of 2, it's worse than that, okay? So the torque of your torque is 4 times as large. What about your rotational mass? Because after all, the angular acceleration, and therefore the whole process of tipping over, is going to be equal to the torque on you divided by your rotational mass. Well, if you remember how rotational mass works, I told you last time that it's assembled out of all the pieces of mass and how far they are from the pivot. And how far they are from the pivot matters a lot. Not moving it twice as far, moving a chunk of mass twice as far from the pivot increases its contribution to rotational mass, not by a factor of 2, but by a factor of 4. Big effect. Therefore, this guy has a certain rotational mass because of all the pieces in here. And in fact, we can say its mass is located here. It's got 1 stick's worth of mass located at the center of mass, which is half the distance away from the pivot. So, okay, if we go to this guy, it's got twice the mass. Okay, so we're working with twice as much mass, but that mass is effectively located twice as far from the pivot. And that, moving it twice as far from the pivot, you don't just use it in proportion to how far it is from the pivot, you have to square that. It contributes 4 times as much every kilogram that you put here, because it's twice as far away. It's 4 times as effective in messing up the rotational mass. So this guy's got 8 times, I hope you can follow that, it's got 8 times the rotational mass of this guy. A factor of 2 because it's got twice the mass, and a factor of 4 because that mass is twice as far away from the pivot. So this has got 8 times the rotational mass, but only 4 times the gravitational torque. It's not going to accelerate as fast as the short guy. Its resistance to acceleration is way up by a factor of 8. And you can feel this too. It's one that you feel these two guys like that, the torque's about a factor of 4. But if you want to go look at the rotational masses, you do this. Whoa, no comparison. It's not a factor of 4, it's a factor of 8. It's big. And the result is this guy tips over much faster than this guy. Okay? That might seem like, oh, fun and games, all fun and games. But here's public service announcement aspect of this. I do these from time to time, whatever. Things that tip over, as they get very long, they go very, very slowly because rotational mass just skyrockets much faster than anything else. And so their ability to tip over becomes hindered by their height. And that means that they experience a lot of internal stresses as they're trying to fall over, and they tend to break. For example, there are famous, I guess I could have pulled these up, there are famous pictures of people taking down industrial chimneys. Like an industrial chimney that might be 200 or 300 feet tall, made of brick. There's a giant chimney west of town out there in the woolen mills area. There's these huge industrial chimneys. I mean, nobody takes them apart brick by brick, or unlikely. They tip them over or blow them up or something like that, right? So there are pictures of them tipping over, and they never tip over and stay intact. The fall is so slow because they're so long, they have such a huge rotational mass that they eventually snap and break during the fall. Okay, the parts, they break off, and the part that's no longer got a pivot at all simply drops. So, okay, that's fun to watch, and it happens routinely. The case where it's a public service announcement is when you're cutting trees, felling trees, be careful. They have a tough time tipping over because they go so slow. And still, it feels like timber, and there are lots of, yeah. They tend to break particularly if they're rotten trees. If you're cutting down a rotten tree that's fragile, it's been standing like this forever, it may be strong enough to tolerate this, but once it gets to this point and all the stress that shows up as it tries to fall over, it can break. And the piece that's at the top then falls straight down. And people get clobbered by the piece coming down. So it is a true hazard when you're cutting trees. Everybody's got horror stories from cutting trees. I certainly have some from my childhood. Be careful with them. And be aware of this tendency for the parts to break and drop because of this rotational physics problem. Okay? All right. That leaves me with one last question. Get this out of here. And then I can go on to wheels. Oh, yeah. So the question is about with the rotational mass, why do you have to square it? Because if you look at the dynamics of how something moves, if I put a piece of mass, suppose this has no mass, this stick, and I clamp on 1 kilogram. If I put it here and I swing it back and forth, it doesn't move very far, and it goes from heading to your left to your right. It's got a modest velocity to your left, a modest velocity to your right. I'm not causing that mass to undergo a very big acceleration, and therefore I'm not noticing the mass all that much. But if I move it to the end, now first off, it's going to move twice as fast. So I'm going to cause it to change its velocity by twice as much in the process of swinging it first one way to the other. And that's going to happen, so twice the change in velocity, and it's going to have to accelerate 4 times as fast. Is that true? Twice. I'm waving my hand here because it's hard to think while I'm doing it. But the change in velocity is much bigger. The effectiveness of that mass in causing me trouble down here goes up not by just a factor of 2, but by a factor of 4 in that. And I'm waving hands, but that's probably the issue. So moving the effective location of the mass of a stick farther and farther from the center dramatically increases its rotational mass. Is that addressing your question? The length is times 2. The gravitational torque is times 4 because I've got twice as much stick effectively located twice as far from my hand. That's 4 times overall. 2 times 2 is 4 times the torque, but you got 8 times the rotational mass because doubling the mass and shoving it twice as far from my hand, I get a factor of 2 for the doubling the mass, and I get a factor of 2 times 2 for moving it twice as far from my hand. Is that okay? So it's huge skyrocketing rotational mass. And you sometimes just grab the sticks and wave them, and feel those effects. This is why, if you remember last time, we had 2 people up here swinging the bars back and forth. And it was putting the mass in your hand, it was easy. Putting the mass far from your hand, much harder. Okay? Yeah, Dave? If you simply took a portion of mass, didn't double the mass, but moved it twice as far from your hand, you would square it. Yes. Yeah. Swinging a golf club, most of the mass is in the head. So if you choke up on the golf club by a factor of 2, you brought you got the same mass as before. You didn't double that, but you brought it half the distance to your hands. Getting it to undergo angular acceleration is now 4 times as easy. All right. Same with bats. I think kids growing up with baseball bats, you learn to choke up on them, because if you're trying to take the full length of the bat, you go get a really long bat that your big brother or sister uses, and you try to swing it. Getting that thing to undergo angular acceleration is hard. So how do you defeat that problem? You don't change the bat; it's got a fixed mass, but you don't use the whole handle. It becomes easier to swing. All right. Once you got it moving, it moves for free. It's inertial, but getting it moving is hard. That requires torque. All right. Oh yes, I did want to ask this question. Okay, so I'll show you the question. Why so slow? Is it doing anything? I don't understand this app anymore. I've lost interest in the app. Okay, I'll just do it, okay? You don't need to vote. We don't need to see it. Here's the experiment, okay? Water balloon, seesaw, mallet, bigger mallet. All right, so when I hit this bar, I used to have students do this, and I used to do it with an egg. And we got a video. Maybe I'll go dig up the video of the egg landing on her head. I'm going to hit this. The question is, this is going to be bad for the balloon. When is it going to be, when's the balloon going to give up the ghost? And if you think about the angular acceleration that's going to occur when I hit this mallet hard and exert a huge force on it, this is going to undergo enormous angular acceleration. The balloon and the bar are going to try not to occupy the same space at the same time by pushing on each other ferociously. When do you think the balloon's going to bust? Okay? It's not guaranteed. I've had it happen every which way. Ready? Get set. All right. No egg, right? Just a little water. It dries. Okay. Sam Silverberg, maybe 10, 15 years ago, the egg exploded as it was launched, and the glob of egg goes up right on her head. Okay, I'll find it. I know where it is. Okay, that's story of seesaws. How about the story of wheels? Okay, just because it is. Story of wheels is really about friction. Hopefully all of you watched the wheels video, but assuming that some of you might have missed it, we use wheels to control friction. We don't use wheels to completely eliminate friction. That turns out not to be a good idea. A car that was just sitting on a block of ice, it can't propel itself forward, it can't steer, it can't do anything good. It's got no, effectively no friction or very little, but it's kind of useless. You actually want to use friction strategically in a car. Of course, if you start out with a car that has no wheels, life is complicated, and particularly if the people are in it. This, my wheelless wagon, I keep meaning to swap the wheels from that wagon to this wagon, because that wagon's had the wheels its whole life, and this one has never had wheels. I feel badly for it. Anyhow, it is experiencing a support force from the table right now. The table's horizontal, so the support force on the wagon is straight up. That's how support forces work. They're perpendicular surfaces. But at the same time, this wagon is capable now of experiencing a different kind of force from the table that is, instead of being perpendicular, this way, is parallel to. Anything at cockeyed angles is a mixture of perpendicular and parallel. So all we need to do is understand the parallel forces in addition to the perpendicular forces. We can do anything. The parallel forces are all known as frictional forces. So they are forces that act to try to bring the bottom of the wagon and the top of the table to the same velocity. So whatever one is doing, frictional forces try to make the other one do the same thing. And let me get this out of there. That means that if the wagon is moving to the left on the table of course is motionless. The frictional force from the table on the wagon pushed it to the right, opposite the wagon's velocity, trying to stop the wagon and bring it to the same velocity as the table. So it was pretty clear that the wagon experienced some sort of force to the right because it stopped. It was going to the left and accelerated to the right, came to a stop. And that's a frictional force from the table on the wagon. And of course, the frictional force is smart. It always fights the relative velocity. So if the wagon's moving to the right, the frictional force pushes it to the left and stops it. Okay? What else about frictional forces? They don't require motion to have a frictional force. In fact, let me put the kid back in here. You can see the frictional forces just by pulling. This gadget here now is showing you how hard I'm pulling. I'm pulling 6 newtons to the left, and yet the little wagon's not moving. So that means the table is exerting a 6 Newton frictional force on the wagon to the right to stop me from making any progress. 10 newtons, 20 newtons, 12 newtons. This is known as static friction. And static friction between two surfaces that are trying to slide but aren't actively sliding yet. Static friction is smart. It can go everywhere from 0 to a maximum. Eventually it will give up. Where is it going to give up on scale? There it went. It gave up. And it got almost to 20 newtons. And then the frictional force gave up and the wagon began to slide. And now I'm only getting 10 newtons of rightward force on the wagon. The point being that the frictional forces seem to come in two categories. The forces between two objects that aren't yet sliding but are trying to, and those are known as static frictional forces. And the forces between two surfaces that are actively sliding across one another, that anybody on the bottom surface would agree the top surface is moving and vice versa. Those are sliding frictional forces. And I'll talk on Monday about the differences, but I've got an agenda here. The two different types of forces have other characteristics that I'll look at. The most important one that I want to look at quickly is that static frictional force wastes no energy. Static frictional force, which is the force that occurs between two surfaces that are not sliding, the force is there, but there's no distance traveled. Nothing's moving. We have to argue about who's moving. We can have both surfaces. Both surfaces can be moving, and then it's a little more complicated. But the basic idea is that one surface does not move across the other, so there's no distance involved in doing work that's worth paying attention to. When there is movement, however, then there is work being done, and it's kind of disappearing. That is, I'll give you the example I gave in the video, and that is if I get the wagon moving by just giving it a shove, it's slowed to a stop, and the energy that I invested in it to get it moving seems to have vanished. It's just gone. And on Monday we'll look at sort of, okay, so where did it disappear? What it disappeared into, it didn't vanish from the universe. It became thermal energy, got all chopped up into biddies and sprinkled around among the surface, the atoms and molecules and the surfaces of the wagon and the table. And we can't do a lot with it anymore. It's now fragmented and hard to work with. Thermal energy is kind of stuck. It's difficult to undo the process and recover what was ordered energy and therefore able to do work. So where I want to go with this is just to talk about a little bit about energy again. I told you about kinetic energies, which is just the energy of motion, right? If I throw the weight, woo! It's got, as it's going horizontally, even though it's not moving up or down, it's got energy just in its sheer motion, kinetic energy. If I lift it upward, it's got a potential energy stored in the forces between the weight and the earth, the gravitational forces. So the potential energies are stored in forces. And so we've got kinetic energy is not stored. It's right there in movement. Potential energies are all stored. That's stored in the gravitational traction between the earth and the block. And here's another potential energy. And this is, you want some nuts, Uncle Melvin? You want some nuts? Right? Woo! There's a snake in the can, right? It's got stored energy. The energy is stored by me right now by shoving the spring. There's a spring in the snake right now. I'm giving away all the secrets. It's stored there. I got one more to show you. Okay? And then you go do it again, right? So put the energy in. It's stored in the forces within this spring. And then, Uncle Melvin, you want to get, woo! Ah! Fooled you again. Boy, you're dumb. Okay. Where I wanted to go with to finish off is the energy stored in another forces, electromagnetic forces. Okay, this guy. We don't do these this semester. This is called a capacitor. This stores energy in the forces between opposite charges. Remember, opposite charges attract? So if you've got positive charge and negative charge really near each other, you have to pull them to get them apart. And then they store energy and love to go back together. And I can't pull them apart with my fingers, but I can use batteries to pull them apart. That's one of the things batteries do nicely. And they're going to pull apart positive and negative charges, assuming these batteries I just chose are good. If not, I'll try another set. So I'm pulling them apart, storing huge numbers of little charges on these two surfaces. And it takes a few seconds to get the job done. It should be done, assuming it worked. And now I'm going to let them get back together. So it didn't look like anything happened, but I did indeed pull apart opposite charges. Ready? Get set? Again? All right. Have to finally get an explosion in this class, right? You can only wait so long. All right. So the batteries are actively pulling apart positive and negative charges and storing them and storing them and storing them. And what I'm doing is letting them get back together with a screwdriver, which has seen better days. Okay? Ready? All right, so the energy was released. It became thermal energy, so it's all fragmented. All right. Okay, so have a good weekend, and I'll see you on Monday.